Hello everyone, welcome back to my YouTube channel. In the previous lectures, we have already gone through the crystallographic point coordinates and directions. In current video, we'll go through the determination of crystallographic planes and their designation. Okay, so the crystallographic planes in a crystal are represented in a manner similar to that of direction, where unit cell acts as the basis and we have a right-handed three-axis coordinate system. Okay, so which is x, y, and z. Okay, okay. So here those planes are defined by the three Miller indices, and these indices are enclosed in round brackets without any separation. Okay, and here what is meant by equivalent planes? Equivalent planes are planes parallel to each other planes that are parallel to each other and have identical indices. Okay, so the procedure to determine the different indices are steps to determine the Miller indices are. Okay, these work for all but the hexagonal crystal. So let us go through these steps one by one. So first is, if the plane passes through the origin, then either the origin should be shifted or the plane should be translated by appropriate unit cell translation or lattice translation. Either new origin must be established, okay, so you can consider any other corner of the unit cell as your origin, or the plane must be translated parallelly by appropriate lattice translation vectors. So, okay, so all in all, it should be made sure that the plane whose indices are to be determined or on which we are working, it should not pass through the origin. So now when you have made sure that the plane doesn't pass through the origin, then we see the crystallographic plane will intersect the three axes, will either intersect or remain parallel to the three axes. Okay, so now these intersections are determined. So for example, A, B and C. These are the intercepts formed by the plane along x, y and z axis respectively. So this A is for x, Y is B is for Y and C is for Z. Now, reciprocal of these intercepts are taken. So, they become 1 by A, 1 by B and 1 by C. Okay. So, the plane which doesn't cut any axis. So, when the plane is parallel to a particular axis, so then intercept is considered to be infinity. Then its reciprocal 1 by intercept that is equals to 0, which becomes the index of the plane along that axis. Alright. Now, after you have got these intercepts, they are normalized by multiplication with the lattice parameters. Okay. So now you have A by A, B by B and C by C. And if necessary, these are to be changed to a set of integers. So for that you can multiply by a common factor n. So they become, so these are the indices. Okay. So now this corresponds to H, this is K and this is L. So now your representation becomes H, K and L. Okay. Okay. Now the crystallographically equivalent planes, sorry, that we'll consider later. Okay. Now let us see some planes and their equivalents. So suppose this is your cubic unit cell. So for this is the x, this is the y and this is the z. So for this particular plane, okay, so you see this particular plane, this never intercepts x or y axis. So intercept along x and y is infinity, infinity and along z is 1. So when you reciprocal it becomes 0, 0, 1. Okay, and if all the lattice parameters are unity, so this plane becomes 0, 0, 1 plane. So the other planes equivalent to this planes, we will be getting those when we translate it by lattice translation vectors. So this is also equivalent to, this is also equivalent to 0, 0, 1 plane. Okay, this is also equivalent to 0, 0, 1. And if we go on to construct another unit cell beneath this, so this plane, then again this will also be equivalent to 0, 0, 1. This is also equivalent to 0, 0, 1 plane. Okay. Now let us see 1, 1, 0 kind of plane. So as you see, to find the intercept, we reciprocal this. So we get 1, 1 and infinity. So we have an intercept of 1 along x, 1 along y, and intercept of infinity along z. So that is, it means it never crosses the z axis. Okay. So for a cubic crystal, so this is your cubic unit cell. So one intercept of 1 along x, so we get an intercept here, and 1 along y, and in z it never intercepts. So this will be the plane. This particular will be the plane, the one shaded in purple. Okay. So this is your 110 plane. Now other equivalent planes can be drawn by translating this by lattice translation vectors. So if you have this another unit cell, then similarly you can get another plane. This is your another 110 plane. So here you can see this is your another 110 plane. Okay. So similar things can continue forward. So now we move on to 111 plane. So here we see the intercepts along different axes are 1, 1 and 1. So along x it is 1, along y it is 1, and along z it is 1. So if I draw a cubic unit cell of unit lattice parameters, this is your x, this is your y, and this is your z. Now if I cut the axes along 1, so this is your intercept, this is your intercept, and this. So this plane must pass through the 3 coordinate axes like this. So this is your 111 plane. Similarly, you can extend the unit cell to get another equivalent 111 planes. So here you can get this. This is your other 111 plane. Okay. Now let us do some solved examples. So going on to example problem 3.11, determination of planar or Miller indices. So suppose you are given a cubic unit cell and this plane. This is your unit cell with the axes x, y, and Z. Now your plane is situated like this. So this is your plane whose indices you need to find. So these are the lattice parameters C, this is B, and this is A. Okay. So let us first find the intercepts. So this is X, this is Y, this is Z. So the intercept along X, so here we see this plane actually passes through the origin. Okay. So we shift our origin to this point. So let us assume this is our origin. So now the new axis system will look like this will be our Z and this will be our X. So we cannot consider this because the plane here passes through the origin. So we need to consider a new origin. So this is our new origin. So with respect to this, the plane actually never cuts the x-axis. So the intercept along x is infinity and it cuts y at minus b. So this is 0, so this is minus b. And it cuts z at c by 2. So the reciprocal will give me 0, minus 1 by b and 2 by c. Now after normalization, or rather I should say after multiplication with lattice parameters, we get 0, minus 1 and 2. Okay. So these are integers, so we need not to multiply or divide them by any common factor. So the indices of this plane are 0, 1 bar, 2. Okay. Now let us move to the next example problem. Three 3.12. It says about the construction of a specified crystallographic plane. Okay. Now in this you need to construct a crystallographic plane as per the given indices, and the indices given are 0, 1, 0. So these are your indices. So H is 1, K is 0 and L is 1. So now as per the formula, A is equals to NA by H. Sorry, you had H is equals to NA by A, K is equals to NB by B, and L equals to NC by C. So you get where these are your intercepts. You need to find the intercepts to construct the plane. So A is A considering n equals to 1, B is 0, sorry, B is infinity as it is 1 by 0, and C is again 1, or sorry, C. So now let us construct a unit cell first. if this is your unit cell, X, Y, and Z. So it cuts, this is your B, this is C, sorry, this is A, and this is C. So intercept along X is A. So it cuts here. The plane cuts here along this, and then intercept along uh, this. B is infinity, so it actually never cuts this y-axis, or it is parallel to that. And intercept along C is again, sorry, along Z is C. So this is C. So your plane is this one. So this is your plane. This is basically your 101 plane. Okay. So this was about the crystallographic planes in cubic crystals. Okay. So now we have family of planes. What is meant by a family of planes? So family of plane contains crystallographically equivalent planes. Okay. So what is meant by crystallographically equivalent planes? They have the same atomic packing. Having same atomic packing. Okay. And that family is designated by enclosing in curly braces. So suppose this is a family, this contains 100, 010, 001, 1 bar 00, 01 bar 0, and 001 bar. So these are the different planes that are contained in this family. So these families correspond to different crystal systems, like cubic has different set of families, tetragonal will have different, orthorhombic will have different, like that. Now let us move to crystallographic planes in hexagonal crystals. So, as was the issue with crystallographic directions of hexagonal planes, for hexagonal crystallographic directions, here also we establish a 4-index scheme, that is H, K, I, and L, to establish equivalence between different planes. Okay, so now because of this 4-index system, we have a more clear idea about the orientation of the plane in a hexagonal crystal. So for transformation from HKL to HKIL, HK and L remains identical and only I changes. I is introduced and it is minus of H plus K. Okay, and the procedure for finding the indices remains the same as described earlier. Okay, so now let us check some example problems to understand the things better. So example problem 3.13. So it says about determination of Miller-Breville indices, that is the 4-index scheme, for a plane within hexagonal unit cell. Okay? Okay. So let us see what plane is given to us first. So the plane that is given to us is okay. So in this hexagonal crystal, we have these axes. This is A2, this is A1, this is A3. Now the plane that we have is this one. It's from here to so this is the plane that we are currently having. So it doesn't pass through the origin, so we need not to shift anything. So first we find the indices with respect to the 3-index scheme, that is H, K, L. So for this, the axes to be considered are A1, A2 and Z. So first we find the intercepts. So A1, A2 and Z. So it cuts A1 at A. So this here, A2 at minus of A and Z at C. So this height is C basically. Okay. Now reciprocal of indices, we get 1 by A minus 1 by A and 1 by C. Then their multiplication with the lattice parameters, we get 1 minus 1, 1. So for a 3-index scheme, the plane indices are 1, 1 by 1. Now for 4-index scheme, we just need to introduce additional parameter of I, that is minus h plus k. So this is minus 1 plus minus 1. So this is 0. So as per 4-index scheme, the indices of this plane are 1, 1 bar 0, 1. So the equivalent indices are 1, 1 bar 1 and 1, 1 bar 0, 1 in both 3-index system and 4-index system. So we see here this index is 0, that means intercept is infinity along A3, and you see it is parallel to the A3 axis. Okay. Okay. So let us check out the summary of crystallographic point, directions and planes. So for point, so coordinate type, then index symbols, and then okay. So for point, we have QRS system, okay, where they are the fractional representatives. Now for direction, we have two different types. First is non-hexagonal where we have UVW system. Then we have hexagonal where we have UVTW. Then for planes, again non-hexagonal, we have HKL, and for hexagonal we have HKIL. Okay, where they are the reciprocal of the intercepts. These are the reciprocals of intercepts along the three axes. They are the intercepts along the axis, and they are the fractions of length along the axis. Okay. Okay. Thank you.